Before we start looking at section 1.2, where it's segments and congruence, we need to go over a couple terms. So we have a postulate or an axiom, meaning the same thing. We'll typically see postulate in this book, in this class. And it's a rule accepted without proof. And usually we're going to read those and say, well, yeah, it's obvious. It makes sense why that's the rule. So that's a postulate. And then we go to a theorem. A theorem is going to be a rule that can be verified with a proof. Now, kind of like the undefined terms we had in section 1 where we just kind of accept them as true, we're going to do that with postulates. Theorems, on the other hand, need a proof. And a proof we're going to learn is an argument that's clear, that uses past known information to verify a new statement. Now, once we have that proof and we've verified it, we can use the theorem anytime we'd like, but it's just a verification that we have to have first. So, our first postulate is the ruler postulate, and this allows us to measure with a ruler. And so it says the points on a line can be matched one-to-one with real numbers. The real number that corresponds to a point is the coordinate of the point. So if we think about having a line here, a number line, and let's say I have a couple points, A and B, and I was to take a ruler and set it down, I could give coordinates to those points. And just imagine two numbers there, whatever they are, 1 and 2, 5 and 7, whatever it may be. So I would use those coordinates to label to it. And even if it was a number line, like you've seen in other math classes, I could give some value to it. And that's what the ruler postulate lets us do. Now, what we'll really use it for is that next part, which says the distance, because the distance between points A and B is the absolute value of the difference of its coordinates. So now I still take this segment AB that has coordinates, let's say they're x1 and x2 still, and it's saying that the distance, how far apart they are, which we write as AB, notice there's no bar or line on top, is the absolute value of their difference, x2 minus x1. We're getting a little complicated in the math, but we have to make sure that it's clear and we follow rules. Let's generalize it. Okay, I have a ruler. I set the ruler down on that segment. Typically I put it at 0 for A. Let's say we put that at 0. Whatever number B is at, that's going to be the distance. And then when we look at the subtracting, well, it's just that number minus 0. Why we have to have the absolute value there is just so we don't say a distance is negative. The absolute value is always positive, therefore distance is always positive. We wouldn't have a distance that's a negative. You come to school, it's so many miles to school. You go back home, it's not negative that amount. It's the same distance, because distance, again, always positive. So if I had maybe coordinates, let's clean it up here. Zero, and then the ruler set down here, it was 5. Well, I'd probably say it's 5 inches, if that happens to be the units. If I had maybe 7 and 13, I happen to set the ruler down so that's where those coordinates hit on the ruler or the number line. How far apart is that? Well, you'd look at it and you'd say, oh, 7, 13, it's 6 apart, so the distance would be 6. So typically, again, we use a ruler, we set it at 0, and then we just find the other value. But if you happen to want to be fancy and set the different points, like 7 and 13 on your ruler, you can still figure out the distance would be 6 units. So that kind of leads us to our next postulate, which is the segment addition postulate. If we can measure a segment and we can give it a distance, then we can also start to add them together. And whenever we think of segment addition postulate, it means we're going to add the parts and set equal to the whole, or the whole segment, or the whole thing. So let's think about this. I have B is between A and C. So let's draw a line here. And point B is between A and C. There's my picture. Does it say B is in the middle? No. It just pretty much means if you started at A and you traveled along and finished at C, you'd pass through B. It's somewhere between there, somewhere on the line. So with this, it says that AC, the whole thing, is equal to AB plus BC. So if I took a whole segment and I broke it into parts, if I added up those parts, it would equal the whole thing. We just talked about a ruler. If I took a ruler and broke the ruler into two pieces. Okay, I have two separate measurements on each of those new pieces, but if I put them together, they still equal the whole. So this is just a basic postulate, and in its basic form, you add the parts, set equal to the whole, but what it's going to allow us to do is start to solve. So if we look down, we have some examples. First up, I need to find RT. RT is the whole thing. So we're not using the numbers, just writing it out. I know that RT equals RS plus ST. Well, what do I know? I know RS is 22. I know that ST is 22. So that by adding those together, I get that RT is 44 units. Okay, we go to the next one. I have XZ is the whole thing. What parts is it equal to? XY and YZ. What do I know? Well, I know XZ is the whole thing is 30. XY, I don't know that one yet. It happens to be what I'm looking for. And I know YZ is 7. So by subtracting the 7, I get 23 for XY, and that's 23 units. Last one. DF is the whole thing. That's equal to the parts DE and EF. If I fill in what I know, 63 is equal to DE plus 50, I find that DE is equal to 63 minus 50, which is 13 units. Okay, now, there's our segments. We're looking at starting to find measurement and length of them. That brings us to the idea of congruence. Now, congruent segments is going to be a very big idea, very big concept, just congruence in general that we're going to see in this class. So if I had two segments here, A, B, and C, D, it says that line segments that have the same length are called congruent segments. So I'm looking at something called length, the same length, let's say equal, and congruence. So if I had two segments that were exactly the same, it's like I took one and copied it and pasted the exact same thing, they would be congruent. So I'm going to put a little mark right here. And these little tack marks means they're congruent. And that tells me that AB segment is congruent to CD. So congruent, we get this new symbol, and this is one you're going to see a lot. You might as well get used to it. This means congruent. Not the same as an equal sign. Now let's think about it. Let's compare them. So if I said they were equal, that's talking about their length, their distance. And if we're doing that, I'm going to say it's inches, feet, centimeters, miles. Then it's really going to be numbers or values. There's an actual something we can put to it. And when I do that, I'm saying that AB, its distance, is equal to CD. Think about the way you drive to school. You travel to school or walk to school, however you get to school. You leave your house, you get to school. You covered some distance, some length. When you come home, if you come home the same way, it's the same distance, it's the same length. So the distance to school is equal to the distance back home. So on the opposite side of that, we get congruence. Now congruent is talking about the actual segment. It's an object. There's no numbers involved. We're talking about that shape itself. We've copied it and created a new version. And that's why we say the segment, notice the bar above AB, is congruent to segment CD. Now, these are saying the exact same thing, essentially. They're connected to each other. With one, you need the other. And in fact, definition of congruence is one we see a lot improves. But we have to start just understanding there's a difference when we look at this picture. Even though these two segments are congruent, we have to remember maybe they're both 5 centimeters. They have the same length, and that's something we'll start to see as we go forward. Now, a good way to look at it is, let's graph some points and draw some segments. So I have A is -2, 4, B is 3, 4, C is 0, 2, and D is 0, -2. So plot the points and determine if they are congruent. So for them to be congruent, we have to know their length. So the length of AB, just write AB, no bar on top because it's a length. I started at -2 and I went to 3. So it's actually 5 units. And you could always count the boxes, 1, 2, 3, 4, 5. 5 units. CD starts at 2 and it goes straight down to -2. It is 4 units. Okay, so AB is not equal to CD. Why? Because one's 5, one's 4. Now, that also means that AB, the segment, is not congruent to CD, and that's because it's not equal. If it's not equal, it's not congruent. Now, let's change the script here. Let's say I took this segment now, and let's call it EF. If I look at EF, it has a length of 5 units. Now, that means that AB is equal to EF because they're both 5, which means that the segment AB is congruent to the segment EF. Because they have the same length, we know they're exactly the same. Okay, so let's change gears now. Now we're looking at a segment addition problem. An important one you're going to see on these problems over here on the right is you have to set up the diagram correctly. So it tells us that point S is in between R and T on segment RT. So that means R and T are endpoints, and S is somewhere between them. Where? We don't know. It's just somewhere between them. Now we know RS is 2x minus 8. We know that ST is 3x minus 10. And we know that RT is 17. Now, it's asking us to solve for x and then find RS and ST. So we're going to set up and make an algebraic equation here, solve for x, then we can plug it back in to find the RS and ST, what they are. Now, before we do that, let's just go through certain things that, if they came up, would be red flags. If I got values for RS and ST that were bigger than 17, that's a problem. Because the whole thing is 17, they should be add up to 17, therefore they're not going to be bigger. I'm also not going to get negative numbers for that. So in the end, it should add together to be 17. So we're going to say that RT is equal to RS plus ST. RT is 17 equals 2x minus 8 plus 3x minus 10. We get 5x minus 18 on the right side. We add 18 to both sides and we get 35 equals 5x. So x is 7. Now we have to solve for each part. RS is 2x minus 8. We plug in the 7. And it looks like 14 minus 8, which is 6 units. Okay, let's kind of think ahead. If RS is 6, what should ST be? Well, it should be 11 because 6 and 11 add to 17. Well, let's go through the work and make sure. And we'll say ST equals 3x minus 10. 3 times 7 minus 10. 3 times 7 is 21. Minus 10 is 11. So ST is 11 units as well. We check, adds up to 17, and we're good.